Okay, hello everybody. Welcome to the session, Streaming AI Workflows in Python, Kafka queues, and Flink-powered LLM interference. Our speakers today have pre-recorded their talk. So if you just allow me 2 seconds to play that on the stage.
Hello, everyone. Thank you for joining me in this talk. We will learn more about streaming AI workflows in Python. My name is Shekhar Rajak. I'm keen interested in open source and mainly contributing different organizations around data, AI, and platform engineering domain. We have Bharat. Yeah, Bharat.
Yeah, hi all. I'm bhrathjatoth, open source contributor and currently working as senior AI architect with Lloyd's Banking Group.
So let's get started. So the agenda is to know and recap how the real-time processing and real-time ML inferencing will work in future. As you know, the batch analytics is very common where we used to run some Spark job or doing some kind of analytics on top of past data to predict something for different use cases. And in now we have real-time ML inferencing AI functionalities like that that Flink provides. And tomorrow, or maybe very near future, we will be having real-time ML Gen AI systems that can understand the events and act accordingly. So the first question that comes in our mind is why it is needed. So let me give you one example. Let's say we are building live streaming application just like Instagram Live or Facebook Live, where users are able to comment anything. And as per our policy, we need to make sure that none of the comments are violating our policies, rules, or any compliance. So what that mean is we need a system which can process millions of users' comment in real time and make sure that none of them are hate speech or violating any policies. So that in those use cases, real-time ML inferencing solve these kind of problems where all the comments will be processed in milliseconds and decide whether we should render those new comments or not. So in concise way, any domain where the cost of being late is higher than the cost of being slightly wrong needs real-time ML call. So business we can think of like fast decision making and deriving some kind of dynamic payment or dynamic pricing of the items and so on. So this is how the typical real-time Flink job looks like, where we get some kind of events from Kafka message bus. We do some kind of operations, data processing, or any kind of enrichment of the data, and then we would like to call an ML API, the ML endpoint, which will do some kind of prediction or inferencing and give some opinion about the event. And later on, we would like to rather whether we can use Iceberg as a data lake or maybe publishing another event that have those inferencing. So let's go not go very far back. Like the Flink AI functions are already available where we can create a model and then it provides Flink SQL function ML predict, using which we can easily do this kind of inferencing. So in this example, this is all about the fraud detection the in the transaction event, and identify if it is any kind of bad event or something like that. So here we can see we already have the APIs like create model and ML predict, but these are all think SQL, not Java API or Python API. Second is this is mainly not actually doing any kind of processing or doing ML calls. What I mean is here we do not have tool accessibility. We cannot add tools. We cannot make sure any kind of agentic workflow here. This is very simple inferencing where every record will be goes to model as a request and model will response back with the prediction and maybe some kind of scoring. So let's see what's new. So yeah, those are the advantages, and some disadvantages comes with the API itself. This provides only the Flink SQL, not the not the correct way of doing the agentic workflow. So the only SQL integration is there. There is retry logic internally available in the Flink AI functions. There are error handlings, and those are asynchronous calls to model. So those are good points about using ML predict and AI functions that Flink provides out of the box. The cons we can think that those are not multi-step reasoning. There are not React agent, no chain of thoughts. We cannot add tools. These are all stateless. Basically, if Flink job dies, then there will be nothing will be stored in a state, and we need to retry calling the model back for the inferencing call. And there are limited providers right now. This is mainly OpenAI or the local models we can use. There is no dynamic orchestration, that means fixed inferencing flow, no branching logic as such. And one more thing, ML predict treat AI like a UDF, a simple stateless and SQL integrated, where contextual retrieval is not required. So in those cases, the ML predict and Flink AI functions are useful. So let's see what is getting built in open source so to solve these. Yeah, Flink agent, Bharat.
Yeah. Thanks, Shekhar. So let me start with a question like why we are building the Flink agents, because the modern enterprise systems are like drawing in real-time events, but today's, as Shekhar said, LLMs are stateless and request-driven and completely disconnected from the moment the prompt ends. So this is where the Flink agents fix this by making AI a native stateful operator inside Apache Flink stream processing runtime. So these Flink agents run always on AI agents on your streaming platform, react to the live events that were happening, and it guarantees you to expect from Flink jobs. And this scale and have millisecond latency and exactly once actions. And they live in a topology, see every event instantly, and maintain the long running context, reason, use tools, and act all exactly, and they scale horizontally. So, just to give you an example, as Shekhar demonstrated earlier, like take an example of fraud detection, which is as a perfect example. So, there are like millions of transactions which stream in per minute. So, Flink instantly computes per user baselines, sliding windows, and anomaly scores. So, the moment a score spikes, the embedded agent wakes up, inspects the full session state, and outputs whether outputs in a less than of 200 milliseconds, like it, and again it is fully replayable and auditable. So the same pattern works for supply chain rerouting and live personalization and many other use cases. So the Flink agents turn continuous streams into continuous intelligence. So that's the reason these are the missing primitive for production grade real-time AI. So coming to the next slide. Yeah, so we have this no, the previous slide, Shekhar. Yeah. So this is once we get the system generated events, it goes to the Flink and it has the embedded LLMs. And we also have the tool calling like with the latest MCP servers and other output events as well. So most like the enterprise AI today is still request and response. Like you ask, it answers, it forgets, which is said earlier. Though we have the context, but that works only for a chart. But whenever it is having in the real time, it is not so feasible, or it is not like an event driven. So that's where these real time Flink agents help. Like these are not any wrappers around the language models, any language models. They are native citizens of Apache Flink's runtime. So what they do is they live inside the stream topology, see every event the moment it happens in real time, and keep the state forever, and all with exactly once guarantees and sub-second latency. So they don't have no fragile glue of microservices and queues. And now a single Flink job can now run hundreds of autonomous agents that detect any of the fraud, any personalized experiences, and coordinate with each other asynchronously like any human nervous systems. So these are like the event-driven Flink agents, which are the new primitive that makes the real-time enterprise AI finally possible. Yeah, next slide, Shikhar.
Okay, so now we have the intros done. Let's go to the more exciting part of the stock, the Kafka queue semantics. As we know, the Kafka is already a messaging bus, but Kafka 4.x come up with queue semantics. So how the traditional Kafka looks like. So we have Kafka topic, we have, let's say, four partitions of this topic, and we want to read these messages from Kafka to the Flink for the processing. We can only parallelize the number of partitions. Basically, the maximum parallelism is not unlimited. Those are bound to partitions count. So one worker is kind of having one consumer, and those will be reading for from one partition. So this is like one partition, one consumer mapping. And if we have more consumers than the partitions, then those consumers will be sitting idle. That is kind of one trade-off in current Kafka world. So why this make why do we have this kind of design in Kafka? Those are all previous to keep 848 and keep 932. So those are having mainly the consumer assignment very static, like per partition. The load balancing is a client side, client side. So whenever there is new consumers are added or older consumers are removed, we are doing some kind of rebalancing of the client side itself. So let's see in Q semantics how this will look like. So when we have Kafka share groups came into picture in Kafka 4, we can extend number of consumers unlimited. So the max parallelism will be can be go beyond. the number of partitions, and the offset management is taken care by the broker manager itself. Even the load balancing will be handled by the broker side automatically. So the client side, the operational cost is reduced, the throughput will be higher, and since we are able to process the events as quickly as possible, the overall system latency will be low. Okay, so till now we went through the Flink AI functions and then Kafka Q semantics, the Flink agent. Let's brainstorm a little bit how the unified real-time AI platform should look like. We are envisioning a system which is having non-blocking ML inferencing. The model lifecycle management will be loosely coupled. We will be having state management and all agentic AI building blocks like tools, resources, and memories. The Flink comes up with fault tolerance. So basically, if something went wrong, something crashed, then it can recover itself. So this is what we want in our AI real-time streaming AI workflow. So let's combine these two ideas about Kafka Q semantics and the Flink agent. So what's going on in the open source? There are some of the works that is still work in progress, where in the Flink connector Kafka, we would like to have Q semantics so that we can increase the throughput and low latency systems we can build through that. So these are the works that is still going on. This also come up with the Python API. So we can easily connect to Kafka share group using Flink connector Kafka Python API. So some of the comments shows how the overall consumption will look like through the Flink SQL. But I will show you how we will be able to do the Kafka share group consumption through the Python API also. As you can see, it just mainly need these configurations about shared group ID, topic, and the parallelism we want. And then um, we should be able to read records with higher throughput. Okay, so I just wanted to quickly touch upon the components that the Flink agent have and the overall demo that we will be seeing. So we have Kafka source topic, which have 3 partitions. And at the end, we have Kafka source operator at the Flink, where basically move to the action executor, which will be the React agent. So basically in Flink agent, we have 2 types of agent. One is workflow agent, where we will orchestrate what we want to do in a sequence. And the second is React agent, which will nothing but reasoning and actions. Basically, it will it will understand the event and accordingly act and observe. So the Flink agent is the building block for event-driven streaming agents. This inherits distributed at scale fault tolerance, structured data processing, and mature state management. So yeah, this comes up with another interesting feature, which is exactly one's action consistency. That means if an agent calls a tool that sends an email or alert event, right? If the job fails, we do not want those events to send again after the recovery. So this makes sure that there is exactly one action. Second, the stateful memory. So if we want to build a rack system, we would like to have all the context in vector store. So the context retrieval request will be sent to vector.db and get the response based on the context. There is multi-step reasoning as well. So basically React loops built in, and this helps in complex tasks without much custom code. So this is the flow that we would like to demonstrate. Exactly, once guarantee, there is recovery, and there is back pressure handling as well. So this makes sure that we are able to have heavy workload and as soon as process as soon as possible, the inferencing as soon as possible. So this is a small code snippet that I have where we will initialize the agent environment and add the resources here using Olama chat model connection. And the Kafka share group API will look like this, where we will set the share group ID, Bootstrap server, and how we would like to deserialize it. There will be React agent, as I mentioned previously, which have the resource descriptor, the chat model details, and about the prompt. In this example, this is sentiment prompt and output schema, where how we would like to output in the console. Or if you want to send back to Kafka, there will be Kafka sync. So when we have the sentiment agent available, we will tie it up with the environment and apply or for all the messages that we have. So I have one recording so that we can quickly see the demo within timeline. So here there is one Flink job running. As we can see, there are number of tasks and we can see the content and the sentiment that is derived by the agent. This is a simple example, but does a lot. So here we can see we can have the source Kafka and the action executor. We had basically a topic which have 3 partitions. And we have share group, my share group with the share group ID. You can see some of the events are getting generated. As we can see, there was 3 partitions for the topic, but their number of workers are more than partitions. That helps in the high throughput and make sure the records are processed as soon as possible. In the log, we can see how it is calling the Kafka share consumer and getting response from the ML API call. Number of tasks which are consuming. So all the workers are getting records, mostly evenly distributed. So yeah, this is what we wanted to quickly show you guys. Okay, I think we will be over time if we'll talk about the iceberg part, but there are some of the features which have branching, time travel, and snapshotting mechanism that can help in different context, and which context helps in better accurate response from the LLM. So this is what we wanted to cover in this section. So thank you so much. Just for the conclusion, we went from run predictions on yesterday's data to autonomous agent responding to events in real time with reasoning capabilities. So there are 3 things we should just recall. Streaming is the new default for AI. Batch is for training. Streaming is for serving. Second, agent needs infrastructure, not just prompt. That means we need all the AI building blocks, state tools, state management, tools, resources, recovery, and how we scale for the overall system integration. Third, Flink agent bridges the gap. All the stream processing guarantees plus the first class agentic AI support. So if you are building AI platforms, start thinking event first. Your user won't wait for batch jobs. Your agent shouldn't either. So thank you so much, guys. These are our LinkedIn QR code, and let's connect.
Yeah, thanks a lot, audience, for showing up.